Welcome to the deep dive. You've sent us some really interesting stuff this time, all about the nitty-gritty of building online platforms that can handle, well, a tidal wave of users.
Yeah, it's a fascinating challenge.
Our goal today is really to extract the core ideas, the smarts behind designing these adaptable systems, without getting totally lost in the super technical weeds.
Exactly. We've got a couple of documents here. We're going to try and pull out the key takeaways.
Right, so you can grasp what's really critical when you're building and running applications designed for, like, massive scale.
Yeah,
Okay, let's dive in.
absolutely. So when you're thinking about platforms for huge numbers of users, the first thing to realize is that a single really beefy server, it'll only get you so far.
Right, eventually you hit a wall.
Yeah, as your user base explodes, you're pretty much inevitably looking at a distributed system.
And what exactly is that, in simple terms?
Well, at its core, a distributed system is basically just a bunch of independent computers, but they're all working together, networked, acting like one single unified system.
Okay, and that immediately brings up some big questions, doesn't it? The material highlighted several key characteristics we need to keep in mind with these distributed setups.
For sure.
First up is scalability, which, I mean, that makes perfect sense. How do you actually cope with more and more people using your platform?
Exactly. And within scalability, there are kind of two main paths. You've got horizontal scaling,
Which is adding more servers, right?
precisely, just adding more machines to spread the load.
That's
That's often what people think of first.
Yep.
Then there's vertical scaling. That's about beefing up your existing servers,
Yeah.
more RAM, faster CPUs, that sort of thing, upgrading the hardware itself.
So bigger servers versus more servers.
Basically, yeah, both have their place. But the key thing here is that while horizontal scaling seems like it offers limitless growth,
Seems being the operative word.
well, yeah, managing a huge fleet of servers introduces significant complexity. Think about deployment, monitoring, keeping everything coordinated. It's a factor people often underestimate early on.
Right, it's not just plugging in more boxes.
Definitely not. Vertical scaling, on the other hand, it's often simpler initially, but there's always a hard limit on how much you can upgrade one single machine. Eventually, you just can't make it any bigger or faster.
That's a really good point about the hidden complexities of managing tons of servers. Okay, so scalability is key. We also looked at reliability and availability. Those sound, well, pretty fundamental for keeping users happy.
Oh, they are absolutely foundational. Reliability is basically the system's ability to keep doing its job correctly, even when individual parts fail. It's about having that built-in resilience.
So it doesn't just fall over if one server hiccups.
Exactly. And availability, then, is the percentage of time the system is actually up, running, and accessible to users. This is where you hear about the nines.
Ah, the famous nines of uptime.
Yep, like 99.9% uptime. Sound pretty good, right? But that still means almost 9 hours of downtime per year.
9 hours. Okay, yeah, that's actually quite a lot if you're running a major service.
It is. Now, boost that to 99.99%,
The extra 9.
and you cut the downtime to just over 50 minutes annually. For platforms with millions of users, those extra nines make a massive difference to the user experience and, the bottom line.
That really puts those small percentages into perspective. What sort of architectural hoops do companies jump through to get from 3 nines to 4? Is it a huge leap in cost and complexity?
Oh, it often is, yeah. It requires significant investment in redundancy, faster failover mechanisms, more sophisticated monitoring. It's definitely not trivial.
Okay. Then we also looked at efficiency, which had these two aspects, latency and throughput. How did those fit in?
Right. So latency is the delay a user sees. It's that pause between making a request, like clicking a link, and getting the first bit of response back.
The loading spinner time.
Pretty much, yeah. Throughput, on the other hand, is how many operations the system can handle in a given time, like
Yeah.
requests per second.
Got it.
And what's interesting is that you often hit trade-offs between these. Like if you really optimize hard to minimize latency for every single request, you might actually limit your overall throughput.
Ah, okay. So trying to be super fast for one person might slow down the system for everyone else if there's a lot of traffic.
It can, yeah. So design becomes this balancing act. You have to figure out what's most critical for your specific application and what your users actually need.
Okay, so we're juggling scalability, reliability, availability, efficiency. It feels like a multi-dimensional puzzle.
It really is.
And then the material brought in the CIP theorem, which seem to suggest we can't actually have it all in a distributed system.
That's a really fundamental concept.
Yeah.
Yeah, the CIP theorem. It states that any distributed system can only guarantee 2 out of 3 specific properties at the same time.
Only two. What are the three?
They are consistency, availability, and partition tolerance.
Okay.
So consistency means all the different parts of the system, all the nodes show the exact same data at the exact same time. Everyone sees the latest update instantly.
Like my bank balance being the same everywhere.
Precisely. Availability means that every request the system receives gets a response. It might not always be the absolute latest, most up-to-date data, but you get a response. The system is, well, available.
Okay.
And partition tolerance means the system keeps working, even if there are network problems that temporarily stop some parts of the system from communicating with each other, like a network partition.
So CAP, consistency, availability, partition tolerance. And you can only pick two.
Essentially, yes. In the real world, network partitions happen, routers fail, cables get cut. So partition tolerance isn't usually optional. You have to design for it.
Right. Networks are unreliable.
Exactly. So that forces a choice, usually between consistency and availability. If you prioritize strong consistency, like in that banking example,
You need the balance to be right immediately.
yes. So during a network partition, you might have to make parts of the system unavailable to ensure consistency isn't violated. You might get an error message instead of seeing potentially wrong data.
Okay, I see.
But if you absolutely need high availability, say, for maybe social media likes or something less critical,
Where it doesn't matter if the count is a tiny bit delayed for some users.
right, you might choose to sacrifice immediate consistency. Different servers might show slightly different like counts for a short time, but the system stays up and responsive. It achieves eventual consistency later on.
So designers have to consciously decide, is it more important for my app to always be available, even if sometimes slightly inconsistent? Or is it more important that the data is always perfectly consistent, even if that means occasional unavailability during network issues?
That's the core trade-off dictated by CAP. You have to understand your application's needs and make that deliberate choice.
Okay, that trade-off is a key insight. So once we have this distributed system, how do we stop one single server from getting completely swamped by all the incoming traffic? That's where the load balancer comes in.
Exactly right. A load balancer acts like a traffic controller. It sits in front of your servers and intelligently distributes the incoming requests across them.
Spreading the work out.
Yep. This stops any one server from getting overloaded and makes sure the workload is shared efficiently. Plus, it adds resilience.
How so?
Well, if one of your servers has a problem or fails completely, the load balancer is smart enough to detect that. It'll just stop sending traffic to the faulty server and direct it only to the healthy ones.
Ah, okay. So it's not just about handling more load, it's also a key part of keeping the system reliable. That makes sense. And the material mentioned that these load balancers can be placed at different spots in the system.
That's right. You don't just have one necessarily. You might have one load balancer sitting between your users and your web servers. Then maybe another set between your web servers and your backend application servers.
And maybe even further back?
Yeah, potentially even between your application servers and your databases. Where you put them depends on where you expect bottlenecks to occur and where you need to distribute load most effectively to keep things running smoothly.
Okay. And they use different methods, different algorithms to decide where to send each request, like round robin or least connection.
Yeah, there are several common algorithms. Round robin is maybe the simplest. It just cycles through the list of servers sequentially. First request goes to server 1, second to server 2, and so on, then back to 1.
Predictable.
Very. Least connection is a bit smarter. It sends the new request to the server that currently has the fewest active connections. The idea is to send work to the least busy server.
That sounds more balanced, maybe.
It often is, yeah, especially if requests take varying amounts of time to process. Then there's also IP hash. This uses the client's IP address to figure out which server gets the request.
Why would you do that?
That's useful if you need a specific user to consistently hit the same server for multiple requests, maybe to maintain some sort of session state directly on that server.
Ah, okay. So the choice of algorithm depends on what you're trying to achieve.
Exactly. It depends on your application's needs and your traffic patterns.
Yeah. Interesting. But what if the load balancer itself fails? That sounds like you've just created a new single point of failure.
That's a critical consideration. You're absolutely right. And the standard solution is redundancy. You typically deploy a pair of load balancers.
A primary and a standby.
Exactly. One is active, handling traffic. The other is passive, just monitoring the primary. If the primary fails its health checks, the standby automatically takes over, usually within seconds.
So you avoid that single point of failure. Makes sense.
Hmm.
Okay, so load balancing handles the initial wave of requests. But what about when those requests keep asking for the same data over and over? That sounds inefficient. That's where caching comes in, right? To speed things up.
Yes, exactly. Caching is a huge performance booster. The basic idea is to store copies of frequently accessed data much closer to where it's actually needed.
Closer than the main database.
Much closer, yeah. The principle is simple. Data requested recently is very likely to be requested again soon. Retrieving data from a cache, which is typically in memory, is way, way faster.
Like how much faster?
Often orders of magnitude faster than going all the way back to the database, which might involve disk reads and network hops. So caching drastically reduces load on your backend systems and makes things quicker for the user.
That makes total sense. Why fetch something slowly from the source if you just got it moments ago? The material mentioned different kinds of caching, like application caches and CDNs.
Right. So an application-level cache usually lives right within or very close to your application servers. It stores data your application frequently needs, maybe results of common database queries or user session information.
Okay, internal to the application. What about CDNs?
CDN stands for Content Delivery Network. These are specifically designed for distributing static assets, things like images, videos, CSS files, JavaScript libraries, things that don't change very often.
How do they work?
CDNs operate a global network of servers called edge servers, located in many different geographical locations. When a user requests, say, an image from your site, the CDN delivers it from the edge server that's geographically closest to that user.
Ah, so someone in London gets the image from a server, maybe in the UK or Europe, not from your main server back in, say, California.
Exactly. This massively reduces latency because the data travels a much shorter distance. It makes websites feel much faster, especially for users far away from your primary data center.
Okay, CDNs for static stuff, closer to the user. But caching in general sounds like it could cause problems if the original data changes, right? How do you keep the cache up to date?
That's the million-dollar question with caching, maintaining data consistency. The cache needs to stay synchronized with the source of truth, usually your main database. You absolutely don't want to serve stale, outdated information.
Yeah, that could be bad. So how do you manage that? The material talked about cache invalidation strategies.
Correct. There are several main approaches. One is write-through caching.
Right through.
Yeah, when data is written, it's written to both the cache and the main database simultaneously before the write operation is confirmed.
So they're always in sync.
Exactly. It guarantees strong consistency. But the downside is higher write latency because you have to wait for both writes to complete. This might slow down applications that do a lot of writing.
Okay. Consistent but potentially slower writes. What else?
There's write around here. Data is written directly to the database, bypassing the cache entirely. The cache only gets populated when data is read.
When would you use that?
It's good if you have data that's written often but rarely read back immediately. It prevents the cache from being filled up with stuff nobody's asking for. But the first read after a write will be slow, as it has to fetch from the database.
A cache miss. Right.
Right. Then there's write back. This is kind of the opposite. Data is written only to the cache initially, very quickly. The cache then asynchronously writes the data back to the database later, maybe in batches.
That sounds fast for writes.
It is. Very low write latency. But it's riskier. If the cache fails before it writes the data back to the database,
Poof. Data loss.
you could lose that data. So it's a trade-off between performance and durability.
Wow. Okay. So different strategies for different needs and risk tolerances. And what happens when the cache just gets full? You can't store everything forever.
Right. You need an eviction policy, a way to decide what data gets kicked out to make room for new stuff.
Like cleaning out the fridge?
Huh, yeah, kind of. Common policies include LRU, FIFO, and LFU.
Okay, acronyms.
LRU is
Exactly.
least recently used. It throws out the data that hasn't been accessed for the longest time. The assumption is if you haven't needed it recently, you probably won't need it soon.
Makes sense. FIFO.
First in, first out. Simple. The oldest data in the cache gets evicted first, regardless of how often or recently it was used.
Okay, and LFU.
Least frequently used. This one evicts the data that has been accessed the fewest number of times. It tries to keep the most popular items.
So again, the best policy depends on how your data is typically accessed.
Precisely. There's no single best policy. It depends on the access patterns.
Okay, we've tackled traffic with load balancers and sped up data access with caching. Now let's get to the heart of it all. the database. The material really contrasted SQL and NoSQL databases. What are the main differences we need to get our heads around?
Right, this is a big one. The fundamental difference is how they structure data. SQL databases are relational. They organize data into tables with rows and columns, and crucially, they have predefined schemas.
Schemas meaning the structure is fixed beforehand.
Exactly. You define the table structure, the columns, their data types up front. If you want to add a new piece of information, a new column, you generally have to alter the table schema for all existing records.
Examples would be like MySQL, PostgreSQL.
Yep, those are classic examples. Oracle, SQL Server 2, you query them using structured query language or SQL.
And how do they typically scale?
Historically, SQL databases scaled vertically, meaning you'd buy a bigger, more powerful server. Horizontal scaling, spreading data across multiple machines using techniques like sharding, is possible, but often more complex to implement correctly.
Okay, and they have those ACD properties.
Yes, a key feature. ACD stands for atomicity, consistency, isolation, durability. It's a set of guarantees ensuring that database transactions are processed reliably.
Can you quickly recap what those mean?
Sure. Atomicity. Transactions are all or nothing. Either the whole sequence of operations completes successfully or none of it does. Consistency. The database always moves from one valid state to another, respecting all rules. Isolation. Concurrent transactions don't interfere with each other. It's as if they run one after another. Durability. Once a transaction is committed, it's permanent, even if the system crashes afterwards.
So ACD means very reliable, predictable transactions.
It's extremely reliable. That's why SQL databases are often the choice for things like financial systems, e-commerce, checkouts, anywhere. Data integrity is absolutely paramount, and where the data structure is fairly stable.
Okay, structured data, ACD guarantees, traditionally vertical scaling. Now, how does NoSQL compare?
NoSQL is kind of an umbrella term for databases that are non-relational. The big differentiator is flexibility. They generally don't require a fixed schema up front.
So you can store different kinds of data within the same collection?
Often, yes. Data structures can vary. There are several main types of NoSQL databases. You have key-value stores.
Like Redis.
Exactly, like Redis or Memcached. Super simple. You store a value associated with a key. Incredibly fast for lookups.
Okay.
Then there are document databases like MongoDB or Couchbase. They store data in document-like structures, often JSON or BSON. Each document can have its own structure. Very flexible.
Sounds good for content or user profiles, maybe.
Definitely. You also have wide column stores, like Cassandra or HBase. Think of tables, but where each row can have different columns. Great for massive data sets with sparse data.
And the last one?
Graph databases, like Neo4j. These are specifically designed to store data points and the relationships between them. Perfect for things like social networks, recommendation engines, fraud detection, anything where connections are key.
Wow, quite a variety. And how do NoSQL databases typically scale?
They're generally designed from the ground up for horizontal scalability. It's often much easier to add more servers to a NoSQL cluster to handle more load or data.
And what about consistency? Do they offer ACID?
Usually not in the same strict sense as SQL databases. Many NoSQL databases prioritize performance and availability over strong consistency. They often follow a model called BASE.
BASE, okay, another acronym.
Yeah, it stands for basically available, soft state, eventually consistent.
Meaning?
Basically, available means the system tries its best to always respond, even if it means returning slightly stale data sometimes. Soft state acknowledges that the system state might be changing over time, even without direct input, as updates propagate. And eventually consistent means that if you stop making updates, eventually all replicas of the data will converge to the same value.
So it might not be instantly consistent everywhere, but it'll get there eventually.
That's the idea. NoSQL databases are often a great fit for handling huge volumes of unstructured or semi-structured data for applications where high availability and massive scale are critical, and where development speed and schema flexibility are important, like big data applications, real-time analytics, content management.
So once more, it really boils down to the specific needs of your application. Are you dealing with structured transactional data needing strong guarantees, or large volumes of flexible data needing massive scale and availability?
Precisely. There's no single best database type. The choice between SQL and NoSQL, and even which NoSQL type, depends entirely on your specific requirements.
Yeah.
Data model, consistency needs, scale, query patterns, even your team's expertise.
Okay. So let's say we've chosen our database, SQL or NoSQL.
Mm-hmm.
How do we make sure our queries actually run fast, especially as the data piles up? The material talked about indexes.
Right. Indexes are crucial for performance. Imagine trying to find a specific topic in a huge book with no index at the back. You'd have to read through every page, right?
Yeah, that would take forever.
It's the same with databases. Without an index, the database might have to scan through every single row in a table to find the data you're asking for. That gets incredibly slow as the table grows.
So an index is like the book's index. It tells the database where to look.
Exactly. An index is a separate data structure, often a B tree or similar,
Yeah.
that stores the values from one or more columns, along with pointers to the actual location of the corresponding rows in the table.
So the database can quickly look up a value in the much smaller index, get the pointer, and jump straight to the data it needs.
Precisely. It avoids that full table scan.
What kinds of indexes are there?
Well, there's usually a primary key index, which is automatically created on the column, that uniquely identify each row. This ensures uniqueness and provides fast lookups by ID.
Okay.
Then you can create secondary indexes on other columns that you frequently use in your search criteria, your where clauses, like maybe indexing the email column in a users table if you often look up users by email.
Makes sense.
You can also create composite indexes, which are indexes on multiple columns together. These are useful if you often query based on combinations of columns, like finding users by city and registration date.
Got it. The material also mentioned foreign keys, but noted they weren't strictly for speed.
Right. Foreign keys are about enforcing relationships and ensuring data integrity between tables, like ensuring an order record always points to a valid customer record. They don't directly speed up reads in the same way indexes do, though they are fundamental to relational database design.
Okay, so indexes sound amazing for speeding up reads, but the material warned there's a trade-off.
Yes, there is. While indexes dramatically improve read performance, selects queries, they can actually slow down write operations, inserts, updates, and deletes.
Yeah, is that.
Because whenever you modify data in the table, any indexes that include that data also need to be updated. If you have lots of indexes on a table, every write operation requires updating the table itself, plus all those indexes.
Ah, so more work for writes.
Exactly. So you need to be intentional about creating indexes. Don't just index every single column. Focus on indexing the columns that are frequently used in your read queries, where clauses or join conditions. Too many unnecessary indexes can hurt your write performance significantly.
Okay, another balancing act. Optimize reads without killing write performance. Now, even with smart indexing, what happens when our database just gets ridiculously huge, like so big it won't fit or perform well on even the biggest single server anymore? That's where database partitioning comes in, right?
You've nailed the next major scaling challenge. When vertical scaling, buying bigger hardware, hits its limit, either technically or financially, you need another strategy. Data partitioning, or sharding, is about breaking that massive database down into smaller, more manageable pieces called partitions or shards.
Why does breaking it up help?
Several reasons. It improves query performance because queries often only need to scan a smaller partition instead of the whole giant data set. It enhances availability because if one partition fails, it might only affect a subset of the data, not the entire system. And it helps with load balancing, as you can distribute the data and the query load across multiple database servers.
Okay. The material mentioned different ways to partition, like horizontal and vertical partitioning.
That's right. Horizontal partitioning, which is often just called sharding, is probably the most common. You divide the rows of a table across multiple separate database instances or tables. Each shard holds a subset of the total rows.
Like splitting a user table by user ID range.
Exactly. Users 1,000 on shard 1, 1,112 million on shard 2, and so on. This works really well for distributing large tables with lots of transactions.
Okay. What's vertical partitioning then?
Vertical partitioning involves splitting a table by columns. You might put frequently accessed columns like user ID, name, email in one table, and less frequently accessed, maybe larger columns like profile, description, last login details, into a separate table, potentially on a different server.
So you split features or data types?
Yeah, it can be useful to isolate different types of data or workloads. There's also directory-based partitioning, where you have a separate lookup service that tells your application which partition holds the specific data it's looking for.
Okay, different methods. And how do you decide which partition a piece of data goes into? What are the criteria?
Good question. There are several strategies for that, too. Key or hash-based partitioning is very common. You apply a hash function to a specific column, the shard key, like user ID, and the result determines which shard the data belongs to.
Hash function.
Yeah, it takes the key and generates a number, which then maps to a specific shard. A useful technique here is consistent hashing, which helps minimize how much data needs to be moved around when you add or remove shards later. It makes scaling the cluster smoother.
Okay. What other criteria are there?
There's list partitioning. You explicitly define which values go into which partition. For example, partition by region. North America in partition 1, Europe in partition 2, Asia in partition 3, based on a country column.
Got it.
Round-robin partitioning just distributes new rows evenly across partitions in a cyclical order. Simple, ensures even distribution, but can make it hard to retrieve related data that might end up on different shards.
Right.
And you can also use composite partitioning, where you combine methods. Maybe you first partition by list region, and then subpartition within each region using hashing on user ID.
Wow, that sounds like it could get pretty complex. The material did mention partitioning comes with its own challenges.
Well, it absolutely does. It introduces significant complexity. One major challenge is querying data that might span across multiple partitions or shards. Joining data from different shards can be difficult, slow, and sometimes requires changes to how you model your data, like denormalization.
Meaning duplicating some data across shards.
Sometimes, yes, to avoid those costly cross-shard joins. Another challenge is rebalancing. When you add new shards to handle growth or remove shards, you need to redistribute the existing data across the new set of shards. This can be a complex, resource-intensive operation that needs careful planning to avoid downtime or impacting performance.
So partitioning is powerful for scale, but definitely not a free lunch. It adds operational overhead and complexity.
Very much so. It's a powerful tool for achieving massive scale, but it needs thoughtful implementation and a good understanding of your data and how it's accessed.
So, wow, we've really covered a lot of ground. We went from, just a single server all the way to this complex interconnected system of load balancers, various caches, different database types, indexes, and even partition databases.
Yeah, it's quite a journey.
It's fascinating to see all the different layers and the decisions you have to make at each step when you're building platforms designed for serious scale. Understanding these core principles really does feel fundamental for anyone involved in, well, building or running modern online applications.
Absolutely. And look, there are countless more advanced techniques, specific algorithms, and nuances we didn't even touch on. But grasping these core concepts, scalability types, reliability versus availability, the role of load balancers, caching strategies and trade-offs, SQL versus NoSQL, why indexing matters, and the basics of partitioning that really provides a strong foundation.
It gives you the mental framework to start thinking about the challenges.
Exactly. It helps you ask the right questions when designing or troubleshooting these high-traffic systems.
Okay, well, considering all these principles we've discussed, what single bottleneck or maybe challenge do you think gets underestimated the most often when people are designing a new online platform?
Yeah.
And why?
That's a tough one.
Something for our listeners to chew on, perhaps, as they look at the apps and websites they use every day. This deep dive has definitely given me, and hopefully everyone listening, some valuable insights into the architecture humming away behind the scenes.
It's definitely complex, but hopefully breaking it down like this helps make sense of the key building blocks.